Recording in progress.
Hello everyone, this is Cyrus from AML 4th year, and my TED Talk topic of computer vision is deep learning for arbitrary shaped water cooling region detection on aerial images. Introduction. Aerial images analysis play a crucial role in diverse fields including agriculture, environmental monitoring, and urban planning. These images provide valuable insights into land use, vegetation health, and infrastructure development. However, one significant challenge in aerial image analysis is the detection of water pooling regions. Water pooling regions are vital indicators of environmental conditions, drainage patterns, and potential hazards. Detecting arbitrary shaped water pooling regions accurately is essential for effective resource management and disaster preparedness. There are some challenges in water pooling region detection that are in the traditional methods of water pooling detection often rely on manual identification or simplicity algorithms. In the previous algorithms, we have to identify the water pooling regions by manually with or by using a simplistic algorithms. But in these deep learning methods, we will overcome the challenges and we will detect, we will identify the regions very clearly and accurately. These methods are labor intensive and time consuming and may lack accuracy, especially for large scale analysis. And these traditional methods are simplistic algorithms suffer are challenging from the lack of accuracy, and also it cannot detect, it cannot identify for the large scale analysis. Limitations in detecting arbitrary shaped water pooling regions arise due to complex and irregular nature of such formalities. Conventional algorithms struggle to accurately delineate boundaries and identify intricate patterns in aerial images. Overview of deep learning. We are going to identifying the water pooling regions by using the deep learning. So before going to that, what is deep learning, how it will be useful to identify the water pooling regions, let's discuss. Deep learning is a subset of machine learning. It involves neural networks with multiple layers. It revolutionize various fields, particularly image analysis tasks by automatically learning hierarchical representation from data. Key components of deep learning includes neural network, computational model inspired by the structure and function of the human brain, consists of interconnected layers of node. And the neural networks, it is same as the human brains. It is the interconnection of neurons. In this, we can say the interconnection of nodes, each node it will calculate and it will analyze the patterns, and finally it gives the output by the final node. And convolutional neural network is specialized neural network designed for processing grid-like data such as images. They use convolutional layers to automatically and adaptively learn spatial hierarchies of features. Deep learning has found widespread applications in computer vision tasks, including the object detection, image classification, semantic segmentation, and more. Proposed approach. We have proposed the YOLO algorithms in these methods to identify the this is comes under the applications of the object detection. So YOLO is the best suitable for the object detection in the deep learning. So the proposed approach leverage deep learning techniques for accurate detection of arbitrary shaped water pooling regions in aerial images. The architecture of the deep learning model comprises multiple layers, including convolutional layer, pooling, and fully connected layers. Convolutional layers extract features from input images, capturing spatial information relevant to the water pooling region detection. So we'll take this data set, and from the images, the convolution layer extract the features uh, input features required for the processing the further layers to accurately identify the water pooling regions. So in the pooling layers, it reduces the spatial dimensions of the feature maps, aiding in feature extraction while enhancing computational efficiency. So in the pooling layer, we will extract the features which is useful to mm, identify the water pooling regions, and we will remove the features which is not useful to predict or to identify the water pooling regions to make this is important layer to make the computational efficiency without consuming the more um, uh, without consuming the more storages. Fully connected layer performs classification, determining the presence and boundaries of water pooling regions based on the extracted features. So in this fully connected layer, it will classify the images to the water bodies regions and non-water bodies regions from the extracted features. So it is helps to classify the images into two classes like water pooling regions and no water pooling regions. The deep learning model utilizes convolution neural network tailored for semantic segmentation tasks. So we are using the CNN convolution neural network because the input data is the images. So I am we'll use the convolution neural network for the image data set. Training involves learning to classify each pixels in the input aerial images as belongs to either water pooling regions or background. So here we can see the some images of the water pooling regions. Here we can see in the A that are the test images. In the B we are seeing that YOLO 4 algorithm version 4 YOLO version 4 algorithm with water 64%. It is predicting as a 64%. Here the 38%. So in the aerial view images, we are finding the water regions. So here we are using the deep learning for the identification of the water bodies. That is the algorithm is YOLO. You only look once. Here we are using RCNN, convolution neural network mask. Here we can it is identifying water whether it is present of water region or not. Here we can see accuracy 0.79 and 0.73 in these images. So these are the sample output images and the input images which is used for the water pooling region identification by using the deep learning methods. Here we can use the we can see the architecture and the flow chart of the how it the entire process of the identification of the water pool region. And here in the initial we will collect the data and we pre-process the images to create data set, and enter we will give the entire training images neural networks. In the neural network they extract the features and it identify the regions, and in the RPN model we'll give it to the RPN model. It will in the model it will identify the regions, and in the fully connected array will classify the objects into water regions and non-water regions. Okay, we are using the dataset. The dataset used for training and evaluation consists of aerial images captured from various sources like irrigation department and geological department. It encompasses a diverse range of landscapes and environmental conditions to ensure robustness and generalization of the model. The dataset is connected with the ground truth labels indicating the presence and the boundaries of water pooling regions. Pre-processing steps are applied to enhance the quality and usability of the dataset. This may include techniques such as images normalization to standardize pixel intensities, data augmentation to increase the diversity of training samples and improve model generalization, mask refinement to ensure accurate annotation of water pooling regions. So after that we will before that we will going to train the model by using the collected images from various sources. The training process involves feeding the deep learning model with the annotated aerial images to train the characteristics of water pooling region. The data sets typically split into training, validation, and test sets to assess model performance and prevent overfitting. Um, During training, the model iteratively adjusts its parameter to minimize the chosen loss functions such as binary cross entropy or Dice coefficient loss. Optimization techniques such as stochastic gradient descent, Adams or RMS props are employed to update the model weights and bias. Hyperparameter includes learning rate, batch, and drop rates are carefully tuned to optimize model performance and convergence. Regulation techniques such as L1, L2 regulations may be applied to prevent the overfitting and improve generalization. Results and discussion. The results demonstrate the efficiency of the proposed deep learning approach in detecting water cooling regions and aerial images. Visual examples are provided showing the detected water cooling regions overlaid with the ground truth annotation. Quantitative evaluation methods such as precision, recall, F1 scores, and intersections over union are presented to assess the model performance. Comparative analysis with the baseline methods or previous approaches may be included to highlight improvements achieved. The performance of the proposed approach is analyzed based on the results of time, strength of the methods such as high accuracy in detecting arbitrary-shaped water cooling regions and robustness to varying environmental conditions are discussed. Limitations such as potential challenges in handling complex terrains are rare instances of classifications are acknowledged potential avenues for future research to address limitations and further enhance the proposed approach suggested. In conclusion, the study represents a novel deep learning approach for detecting arbitrary shift water cooling regions and aerial images. Key findings. In this, we are finding the achievements high accuracy and robustness water cooling regions detection, demonstrating the effectiveness of deep learning in handling complex environmental conditions and highlighting the potential for automated analysis and monitoring of water-related phenomena in aerial imagery. Deep learning has shown significant promise in improving water pooling regions detection, offering benefits such as enhanced efficiency and accuracy compared to traditional methods, scalability for large-scale aerial images analysis, potential applications in various fields, including agricultural, environmental monitoring, and disaster management. Thank you.